So in this video, I wanted to talk about something we come across in abstract algebra called cyclic groups. Previously, we learned that a set G combined with an operation is a group if it's associative under the operation, closed under the operation, it contains the identity, and all of the elements have inverses. So this is true for all groups, and a cyclic group is a special type of group such that the group G is generated by an element in G. So a group G is cyclic if one element generates all the elements. So we can also write this, so G is equal to A. This is equivalent to saying G is equal to G is the group generated by A. So this is also equivalent to saying G is equal to A to the n, where n is an integer. So this definition, G, a cyclic group G, is equal to A or a base raised to an integer, is going to be important to note when you're trying to prove things involving cyclic groups. So let's look at this theorem and a proof for this theorem. So we're going to let G be a finite cyclic group. So it has a certain number of elements, and here we're going to say the number of elements is n, so of order n, meaning there's n number of elements, and it's generated by A. And we're also, well, let's just say that. Let's end it right there. So G, this is what we've been given so far, basically. G is generated by A. So for each integer m in Z, the group generated by A to the m is equal to the group generated by A to the D, where D is equal to the GCD, the greatest common divisor of m and n. Remember, n is the order of G. Okay, so this is a theorem, and I think proving this will kind of start to get us more comfortable with dealing with cyclic groups and their properties. So let's start this. Let's start this proof. And if you look at this theorem and you were asked to prove it and you're not really sure where to start, and it just seems a little overwhelming to you because you're kind of given a lot of information, it feels like you're here, just know that whenever you're approaching a proof, when you start it, you don't necessarily always know exactly where the proof is going to go. So you may do a rough draft and go down one road and it doesn't lead you anywhere, and you may need to go down several roads before you find your aha moment. Here, what jumped out at me is that we are trying to prove an equality. So we want to prove that the group generated by A to the m is equal to the group generated by A to the D. So first and foremost, let's write down our knowns. So we're going to let G be a cyclic group of order n. That was given to us and generated by A. So that was given to us. And we're also going to let m be an integer such that the GCD of m and n equals d. So those are just our givens. So if you're ever starting a proof, just go ahead and write down what you're given. So then you can kind of see, okay, I've got the order of G is n, I know the GCD of M and N is D, and I'm trying to prove an equality. Well, whenever you're trying to prove an equality, something you can always try and almost always works is element chasing. So what I mean is if you first show that A to the M is equal to the group generated by A to the D, that this is a subgroup of that, and you also show that A to the D generated is a subgroup of the group generated by A to the M. If you show both of these, this proves equality. So let's first start with this containment here. So let's first start with this containment. So we're going to let's pick an arbitrary element, x, be an element of A to the M. Now remember our definition of a cyclic group was that a group generated by something is that something raised to an integer. So this is our definition. So if we apply that definition here, if x is an element of this group, then we know x is equal to, and remember the definition of a group generated by something is just that something raised to an integer. So we're going to say, let's say k here. Okay? So A is equal to mk. We know we can write that just by law of exponents. And this is where k is an integer. Okay? So we're trying to do left side containment. We saw that A to the M is a cyclic group, so we use the definition of cyclic groups to rewrite this x is equal to A to the mk, okay? So now we're trying to incorporate D. So since we know D is equal to the GCD of M and N, by definition of GCD, I have another video on GCDs if you want to look at that, but we know since D is the greatest common divisor, it divides M and N. So we know D divides M, and thus there exists an element L in Z, an integer, such that M is equal to DL. And that's just using the definition of GCD and also using divisibility rules. Okay, so now by substituting, we have x is equal to A to the mk equals A to the substitute DL for mk. And now just exponent rules say that we can rearrange these because these are just integers, and integers are associative under multiplication. So we can say this is equal to A to the D to the LK. All right. So now we have x is equal to something, A to the D, raised to an integer. Now remember, the definition of a cyclic group is just the base raised to an integer. So this is the definition of the group generated by A to the D. So we can say, thus, x is an element of the group generated by A to the D. And since we said x was an element of A to the M, we know that A to the M is a subgroup of A to the D. Okay? So now we have this containment down. So let's start the right side containment. So here, we just want to say, we want to do the right side containment. All right. So now let's let x be an element of a to the d. Because now we're trying to show, remember we're trying to show that now that the group generated by a to the d is a subgroup of the group generated by a to the m. So now we're going to, kind of go the opposite way and let x be an element of a to the d. So x is equal, just by definition of cyclic groups, a to the d to the k for some k and z. So similarly, we're going to kind of go down the same road. Since d is equal to the GCD of m and n, we know that there exists r and s and z such that d is equal to mr plus ns. Okay? So we know by definition of greatest common divisors of m and n that d will just equal a linear combination of m and n where r and s are integers. And that's just using the definition of greatest common divisors. And I go over that in my greatest common divisors video if you want to review that. So now we have an expression for d. So by substitution, we have x equals a to the mr plus ns, just subbing that in for d, to the k. And if we just distribute that k, we have a to the mrk plus nsk. And just by exponent rules, we can write that as a to the mrk times a to the nsk. Okay, now this next part that we're going to do, this next fact we're going to take to get us to the next step of our proof is one that is really important. I'm going to write it in blue. And you're going to use this fact for so many proofs when you're dealing with cyclic groups. And this is just using a definition from a cyclic group, a theorem that maybe we can prove later. If you go in any abstract algebra book, you can find this this fact. So we're going to say, since, remember earlier in the problem we said the order of G is equal to n. So G, where G is a group generated by A. So A generates the group G, and there are n elements. So since these two things are true, we know A to the n is equal to the identity. Okay? So if you have a group generated by A, and it's a finite group with order n, you can always say that A to the n, A raised to the order of G. So you can say, in general, A raised to the order of G equals the identity. Okay? So since we know this fact here, and we have A to the n right here, we can say x equals, we'll just rewrite these exponents, and we can do this using exponent rules. That's just rewriting these exponents here. So we know A to the n is equal to the identity. So this just equals A to the m rk times the identity to the sk. And the identity raised to anything is just the identity. So this is just going to be E. And then the identity times anything is just that thing. So this is just going to equal A to the m rk. So that gives us something that's very helpful because we know now x is equal to A to the m rk. So by definition of cyclic groups, we have A to the m raised to an integer r times k. So by definition, we can say, so x is an element of the group generated by a to the m. Here to there. Thus, a to the d is a subset of a to the m. So we proved that the group generated by a to the d is a subset of the group generated by a to the m, and we also proved the converse of that. So since we proved that each were a subset of the other, we have proved equality. So therefore, a to the m is equal to a to the d. And that concludes that proof. So what we were given was that we knew G was a finite cyclic group of order n generated by A. We knew that D was equal to the GCD of M and N, and we wanted to prove that this group generated by A to the M was equal to this group generated by A to the D. And we just took our knowns and we took some facts about cyclic groups and greatest common divisors, and we went through and we proved that each were a subset of the other. So we used element chasing and we got the end result. So if you have any more questions about cyclic groups, feel free to leave a comment.